So therefore, we're going to end up with different types of covalent compounds. All right, and so in these two cases, we're just looking at methane, and these are all the different ways we can represent methane. And this is water, all the different ways we can represent water. Okay, and we represent them in these different ways depending on the point that we're trying to make. So we go from the Lewis structure to the shape of the molecule to the space-filling model to the electron cloud distribution. So if we're looking at these molecules, we want to know, we know they're covalent compounds because they're, nonmetals and nonmetals, nonmetals and nonmetals, but we'd like to know, which types of covalent compounds are what we would call polar covalent compounds and which type are nonpolar. And how can I tell just by looking at these structures whether or not this is polar or nonpolar and whether or not this is polar or nonpolar? We're going to answer that question. Come back to that picture. Okay. Well, first of all, before you can determine if a molecule is polar or nonpolar, you have to understand if the bond itself is polar or nonpolar. And so this idea of electronegativity is the measure of an atom's attraction for the electrons it shares in a covalent bond. So we can use the concept of electronegativity to determine whether or not the bond itself is polar. And once we figure out whether or not the bonds within the molecule are polar, then we have to take one more step to determine if the molecule as a whole is polar. So first we're just focusing on the bonds, polar covalent bonds. Covalent bond in which electrons are not equally shared, but rather displaced towards the more electronegative. So when we talk about the atom that has the greater attraction for the electrons, the technical term for that is it's more electronegative. And there's a table or values, electronegativity values shown in this table right here. Different atoms have been assigned this is a relative scale, electronegativity values. And this is just a bit of the periodic table, and this is an element, and below the element is the electronegativity value for that particular element. And this is just a small snapshot of the periodic table. But in general, as you move from left to right across the periodic table, across a row in the periodic table, the electronegativity value increases. And in general, as you move up within a group from bottom to top, the electronegativity values increase. And you can see that trend in this little snippet of the periodic table. The element that has the highest electronegativity value is fluorine with 4.0, and not shown on this table, but the lowest value is cesium with 0.7. Okay, so as you can see, it increases as you go across and over, and the electronegativity is the measure of the attraction that that particular atom would have if it were involved in a covalent bond with another atom. All right, and then also notice here the noble gases have no value. They have no electronegativity value because the octet is satisfied in noble gases. They have no attraction for another atom in a covalent bond because they don't form covalent bonds. Okay, all right, so that's this idea of electronegativity, and these are values. And we can use these electronegativity values to help us determine whether or not a bond is polar and what degree of polarity is. The bigger the difference in the electronegativity value between the two atoms, the more polar that particular bond is. So in this case, we're looking at an OH bond, and what you see is this is the electronegativity value for oxygen from that table, it's 3.5. The electronegativity value for hydrogen from the table is 2.1. And so the difference in electronegativities between these two atoms and this particular covalent bond is 1.4. And in general, if the difference is greater than 0.3, one would consider the bond to be polar. So we would consider this a very polar bond. And again, you see a lot of times when these polar bonds are drawn, they're drawn as a vector. And the vector would have a direction and a magnitude. And the magnitude is the electronegativity difference. And the direction is always in the direction of the more electronegative atom. And in this case, more electrons would reside on this atom than that atom in this particular bond. And so that's why this one is given the delta negative, indicating that it has more electron cloud density, and this would be the delta positive. Or sometimes we say partially negative and partially positive, because this isn't an ionic situation where the electron has completely left this atom and been accepted by that atom, but it is sort of transitional in that the electrons are not equally shared. Okay, so this is how we define whether or not a bond is polar based on the electronegativity difference between the atoms in the bond. And this is some of the symbolism that is used. Okay,